Hello everybody, this is your midterm study guide video. So welcome, we're going to do this in two parts because you do have a pretty long study guide. There are about 80 questions on there, so we'll go about 40 of them today. And then we'll do another video with another 40. You'll be all done and getting ready for your midterm. So just to give you some information here that get you all prepared. So let's go over just kind of the starting stuff here. So your midterm is coming up. You're going to have about 1 week to take it, okay? And that will include a Saturday. They're not open. The testing center isn't open on Sunday, but it is open on a Saturday, so you can go there. So your midterm is going to be worth about 120 points. It'll have about 60 questions. Now, the way this is going to work is that there will be a test bank. What's a test bank? Well, it's going to be, or in other terms, a question bank. So a question bank is when you have actually every single question that's on this midterm study guide that you're looking at is on the question bank, okay? The test is going to automatically select 60 of those. So you have 80 questions here, and it's going to select 60 of those, okay? So does that make sense? So most of what you see here today is going to be on the test. So I'm literally giving you the test questions, all right? And I'm giving you right now the answers to the test questions, so good to pay attention. Where do you take your test? So I don't do online tests, so I don't do any of the Respondus or lockdown stuff. I've had too many academic honesty issues. I don't trust in them, so I don't do them. So you have to take your test at the testing center. There's the address of the testing center. It's near Heritage Campus on Ayers Street, and you have to sign up with them. You're going to have, like I said, 1 week to take it right there. And the testing center is typically open from like 8 a.m. to 4:30. They have different hours on Friday and Saturday. They are open on Saturday. You must register for this test 24 hours in advance, though. So you can't just show up. They don't take walk-ins. You have to register beforehand. So really don't procrastinate. The slots fill up early. So if you're watching this right now and you haven't registered, go and just make an appointment right now, because what you want to avoid is it's the last day to take the test and you still haven't made an appointment. Then you're in trouble. Okay, so if you haven't done it now, just go register for a slot. And if you can't make it, just call them. And their number, do I put their number? Well, it's easy to find their phone number. I should put their phone number on here. It's easy to find their phone number. Just call them and let them know you can't come and schedule another time. It's not a big deal. So anyway, this is the link to where you can register. I have another video you can watch that kind of walks you through how to register if you can't figure it out, which is fine. Also, in addition to that, I will hold right here, you can see, maybe 1 or 2 times for walk-ins, okay? And I'm going to do that at the OSO campus. So if you haven't been to the OSO campus, it's a good opportunity to check it out. I'll be there at the OSO campus, and the room is ST339. So it's the STEM building, room 339. It's up on the 3rd floor. Okay. This is a closed book, closed note test. Oh, and by the way, regarding walk-in times, I'm going to put out an announcement, with that time. Okay. So it kind of depends on what my schedule is, but I'll have maybe 1 or 2 times I will be available for walk-ins to take that test without an appointment. It'll probably be near the end of the testing time. Okay, this is a closed book, closed note test. Okay, so it's just all your memory. And so this is an exercise in lots of facts about the Earth, about geology, and getting them into your head and remembering them. So I don't allow it's closed note, closed book. So you're going to come in just with, you can have a scratch paper and a pencil, and that's all I allow. So you will not need a calculator. So it's just a matter of learning and memorizing facts about the Earth, about geology. There'll be different question styles. You will have some open response questions, which will consist of maybe like 1 paragraph, writing 1 paragraph about a certain question. You'll probably have like 4 or 5 of those. It kind of depends, on the questions that come out of the bank, which are randomly chosen. So you could somehow be lucky and have none of those, but you could have, I think, maybe up to 6 there are. So, but you probably on average you'll end up with like maybe 4, right? Because you're going to get 2/3 of the questions really. 2/3 of the questions from the question bank. All right, so there'll be matching, there'll be open response, like I said, there'll be multiple choice, there will be some multiple answer ones where you have to like select everything that applies, things like that. So probably stuff you're not, you won't be surprising to you. It's pretty standard. Okay, so anyway, that's the test. That's the description of the test. Go to Canvas site to get specifics about times and dates for the test, okay? So anyway, let's go and actually get into the material, right? Go do 40 of these questions today. We'll save the other 40 for next time. So what should you know for this midterm? Okay, first of all, our first lecture was on philosophy of science. So philosophy of science, what I really want you to know is the limitations of science. That was kind of my big thing about this lectures. I wanted you to understand that science doesn't answer every question, right? So the first question here, right? Can you answer every question with science? No. In fact, you can't even answer that question with science. You can't do a scientific research and publish an article about whether science can answer every question, because that's not even a scientific question itself. It's a philosophical question. But the fact of the matter is, it cannot answer every single question of the universe, right? There's certain things it can look at, and there's certain things it can't look at. Certain things that science can see, and certain things that science is blind to. So that's false. Here's a possible short answer question. I would like you to give me a question that is building off of what we just talked about. That is impossible for science to answer. It's impossible to answer it scientifically. Please ignore things like technological limitations. Focus on rather a kind of question that cannot be answered by science. Write your question below, describe, and be able to describe why it can't be answered by science. Okay, so what kind of things would be good to put here? Questions about meanings of words. Any question about meaning. What does this word mean? What does this term mean? What is the even asking things like, what's the definition of energy? What's the definition of matter, space, and time? Although those are subjects that we study with science, we can't answer. Science itself can't tell you the meaning of those things are. Okay, well, that's a matter of philosophical debate. What we mean by those words. Things about any philosophical questions about moral truth. Questions about anything. For example, I notice a lot of people put kind of religious questions. That's counts too. It's things like anything philosophical. So, for example, questions like, what's the meaning of life? People kind of felt hokey putting that down, but that's a great question to put there. Science we can't measure an atom or something and get an answer about what the meaning of life is, right? That's obvious. So anyway, any question like that, remember that to be a scientific question, you have to have three things. You have to be falsifiable. And what does falsifiable mean? It means you can prove it true or not true, by what? By physical evidence. Physical evidence, physical observations of matter, space, time, energy, etc., etc., etc. Okay, those are the elements that are studied by science. Okay, it has to be falsifiable. I'm trying to give myself some more room here. It has to be reproducible. That means other people have to be able to go and reproduce your own results for your own scientific experiments. It has to be also physical and empirical. What does empirical mean? Empirical means based on observation. It means something that you can observe. Okay, that's the bottom line. It has to be something that you can observe. What's the difference between a hypothesis and a prediction? Moving on to the next question. So this is another question I often ask because I notice that people confuse the two a lot. To give you an example of that, this is something I see a lot of people say, or even written in textbooks. Let's do an experiment. Okay, what do you think is going to happen? What's your hypothesis about what's going to happen? That's not right. A hypothesis is an explanation of how something works. How nature works, I should say. Okay, it seeks to explain and answer why. Okay, why? A prediction is different. A prediction is, I mean, you already kind of know what a prediction is. A prediction seeks to guess what's going to happen, right? It's a guess of what will happen. And a very easy way to think about this, a prediction cannot answer the question why. It can tell you, it seeks to explain rather what will happen. So predictions are kind of more like what is going to happen. It's a question that says something like what is going to happen. It explains what's going to happen. It's more of a what question. A hypothesis, on the other hand, is an explanation. It's a proposed explanation that doesn't have very much evidence to back it up yet. So once a hypothesis gets more evidence to back it up, we elevate it to a theory. And then from a theory, we can elevate it. And once it becomes very, very certain based on physical evidence, then we can elevate it to a natural law or law. Okay? So there's a progression there. A progression of certitude. So from a hypothesis, you go to a theory, and then theory to a law. But a hypothesis always seeks to explain why something happens and how nature works. It's explaining how nature works. Okay, it doesn't guess at what's going to happen. Okay, predictions do that. So that's the difference between prediction and hypothesis. What's it mean that science is empirical? Very, very simple here. Observation. Science is based on observation. That's what makes it empirical. That word empirical simply means based on observation. Okay, that's all there is to it. Based on observation. What's the difference between qualitative and quantitative reasoning? Or I should say, this really should not say reasoning. It should say observation. I'm sorry for that. So qualitative reasoning, or said it again, qualitative observation. Qualitative observation is based off of, you're making observations that are of qualities. These are things like shape, color, form, just things that cannot be measured. You cannot be measured very well or very accurately. Okay. Quantitative, for example, is based on quantities. So quantities are things that are measurable. Okay, so for example, the temperature. What's the temperature? A qualitative observation, somebody might just say it's hot or it's cold. But a quantitative, we always prefer quantitative as much as we can in science. We'll be more specific. They'll measure something. So they'll say, not only is it hot, it is, 40 degrees Celsius. Not only is it cold, that's qualitative. Quantitative will say it's, negative 10 degrees Celsius, whatever. Okay, so that's the difference between those two. And fairly simple. Most people understand that without too much trouble. Okay. Now, on to the metric system. We talked about the metric system. Base metric system units. You should be familiar with your base metric system units. Time is measured in seconds. Distance is measured in meters. Mass is measured in kilograms. For long distances, what do we use? Kilometers, right? For short distances, what do we use? Centimeters or even millimeters, okay? So you should know those base units. Now, what are some of the advantages of the metric system over the English system? That's a possible short answer question. And one of the things about the metric system, I hope you remember, is that what you have is a base unit. Remember, there are different dimensions of the universe we can measure, things like temperature, mass, distance, time, etc., etc., etc. And for each of those different dimensions that we can measure, we have a base unit in the metric system, right? So that's what we just talked about up here. Space is measured in meters, right? Time is measured in seconds. mass is measured in kilograms, et cetera, et cetera. Then we're going to scale that up to different we can scale it up or scale it down by factors of 10, right? So what we can have is, for example, a deci prefix, and that scales it down by a factor of 10 to the minus 1, or 0.1, okay? So a meter, let's say we're just talking about meters, we could have a decimeter, right? And that is 0.1 meters, okay? You could have, after that, a centimeter. That's 10 to the negative 2, or 0.01 meters, right? You could have a millimeter, and that's 1/1000th of a meter, 0.001 meters, right? That's a millimeter. All right, so what's the advantage of that over the English system? Well, everything is related by factors of 10. It's not true for the English system. The English system, or aka the imperial system, you have different factors relating different things. So, for example, let's go to an English system, right? Miles. Okay, 5,280 feet in a mile. 12 inches per foot. Okay, and then if you get down to smaller than inches, I guess we start dividing up inches. We don't really have a good unit for in the imperial system of really small things. Let's say that we get to go beyond miles, but I don't know if we I guess in the English system we don't even have anything beyond miles. So and that's a problem too. So you're kind of limited in the English system in terms of big distances or small distances too, right? We don't have a good unit. What if you wanted to measure the length of an atom? What would we do in the English system? Point 0.000000000000001 inch, something like that. That would be really annoying. It's really easy in the metric system because we can just say the length of this atom is, 1.2 picometers or something like that, which is a very small unit. But anyway, that's the advantages. It makes conversions simpler. It can apply to very large distances or large dimensions and very small ones. It can also stops you from having to write a lot of zeros, right? Either 0.0000012 or something, or 1,000 0.0000000 pounds or something. So anyway, those are the advantages you should be familiar with, and just make sure you have some basic understanding of how the metric system works. Okay, you will have maybe some very simple, not requiring a calculator, metric system conversions. Okay, so for example, a person's height is 1.561 meters. How many centimeters is that? How many millimeters is that? Okay. Now remember, with metric system conversions, it's easy because all you're doing is moving the decimal point. Now remember how things work. You have the base unit. You have the different prefixes. You have deca, centa, milla. Okay. That scales it down by factors of 10. So if we have 1.561 meters, that's the base unit. We want to convert that to centimeters. We're going to jump 1, 2, okay? And we're going to move, because we're going from a big unit to a small unit, we're going to move the decimal point to the right, and we're going to move it 1, 2. And so you end up saying this is equivalent, 1.561 meters is equivalent to 156.1 centimeters, okay? If we do an extra jump down to millimeters, we jump one more time, and then that is equivalent to 1561 millimeters. Okay, so that's all there is to it. You're just moving, and that's why you don't need a calculator. A calculator doesn't even help you with this, right? You're just moving the decimal point. Given that there are 22 pounds per kilogram, 2.2 pounds per kilogram. How many kilograms is in 22 pounds? Again, this is something, it might seem like, I need a calculator. You don't need a calculator for this. It's just moving the decimal point. So there are 2.2 pounds per kilogram. I'm giving you the conversion factor. You don't have to remember conversion factors between English system units and metric system units. How many kilograms is 22 pounds? So in this case, 22 pounds divided by 2.2 pounds per kg hopefully you can see that these are related just by a factor of 10, right? So that equals 10 kg. Okay. Given there are 1.6 kilometers per mile, how many kilometers is in 16 miles? So it's the same thing, right? 16 miles divided by 1.6 kilometers per mile. Actually, yeah. 1.6. Wait a second. I'm getting myself all confused. How many kilometers is in 16 miles? Oh, I see. So this is actually should be backwards. So you have 16. Sorry, I made a mistake when I wrote this. I realized I put this thing. See, this should be backwards. I'm sorry. It was like, wait, this isn't right, because it needs to be easy, easy math. So, how many miles is in 16 kilometers? That's the way it's supposed to be. I'm sorry for that. 16 kilometers divided by 1.6 kilometers per mile. Again, the math works out easily. It's just 10 miles. Okay, so there could be a question something like that, but it would be easy math that wouldn't require a calculator. Okay, it's like, for example, this one was just 22 divided by 2.2. Hopefully it's, I guess, I don't want to make anybody feel bad, but hopefully it's fairly obvious or fairly apparent to you. You can do that kind of math without a calculator. It's just, 22 divided by 2.2 is just 10, right? So it should be something pretty easy. Maybe I could give you another example. Maybe I have like 4.4 divided by 2.2. Hopefully it's fairly obvious to you. The answer to that is 2, right? I hope. I'm sorry if it's not, but hopefully it is. Okay, what is density? Density is the mass to volume ratio. There, okay? So it's how much mass is in a given unit of volume, okay? Different materials have different densities. The density of water is 1 gram per cubic centimeter, okay? 1. Most rocks, on average, have densities of around maybe somewhere between 2 to 3, or maybe 2 to 3.5 grams per cc. Average, probably something like, 2.75 grams per cc. Okay, so I want you to have some understanding of like average densities of water, because water is kind of a base reference unit we use, and then of rock, which is about 2.75. Okay. All right, so that's metric system. Now going on to global geography, at a lecture on geography on latitude and longitude. Hopefully you understand that and remember some of that. So lines of longitude, remember, going from pole to pole, are called meridians. And the lines of latitude that go across, okay, so remember, lines of longitude, meridians, go like this, okay? Lines of latitude go like this. All right, they go straight across. So don't, a lot of people like to draw things like, they get confused and they start drawing. I notice on the drawings, people start drawing parallels. These are called parallels. They start drawing parallels like this, curving like this, and then they were drawing lines of. So that's actually totally wrong. It doesn't look like that. The parallels are parallel, right? They're all parallel. Do you notice how if you curve them, they're no longer parallel with each other? Okay, they're parallel. They're straight lines that go straight across the earth. I guess you don't need to know that for the test, but it's just pet peeve, I guess. Okay, what's the tilt of the rotational axis of Earth? Make sure you know that, 23.5 degrees. So that means that we're tilted somewhat relative to we're a little bit off kilter relative to our orbital plane, okay? By 23.5 degrees. And that does change over Earth's history. It actually goes from anywhere from 22.5 to 24.5. So we're kind of at an average tilt right now. Now, during the summer solstice, sun is directly overhead which parallel? So during the summer solstice, I'm going to draw Earth here, And here's the sun over here. Okay, the light rays from the sun are coming in, and they are shining directly overhead. Okay, I'm going to kind of draw the tilt of the Earth's axis like this, and they are directly overhead at the Tropic of Capricorn, or sorry, Tropic of Cancer. And then in the winter solstice, they're over the Capricorn. Okay, those are the tropics. Hopefully I didn't get them mixed up. I gotta go check now. I can't remember exactly which ones. Let's see. Tropic of Can't remember which one's which. I don't want to tell you the right. Yeah, okay. Tropic of Capricorn's in the south. So is that one? Yeah, I did it right. Okay, Tropic of yeah, it's Capricorn's in the south, Cancer's in the north. During the winter solstice, sun is directly overhead. Which parallel? Capricorn here. Okay. During the summer, it's over Cancer. Okay. During either equinox, the sun is directly overhead. Which parallel? Now, during the equinox, the Earth is like this relative to the sun. It's directly upright. Okay, so the sun is directly overhead the equinox, or equator. Sorry. So that one's pretty easy to remember because equator, equinox, right? So they're same kind of beginning words, so you should be able to remember that. So over the equinox, sun is directly overhead the equator. Okay, so those are, we actually, you know, if you're in fall, right? Fall starts with the autumnal equinox. If you're in spring, it starts with the vernal equinox. Okay. All right. There's another question you should know. What's the climate like at high latitudes, above 66 degrees north or 66 degrees south? What's it like? It is cold, right? You know, it's in the poles. It's cold. Arctic circle, Antarctic circle. It's cold, right? What about low latitudes around the equator? It's hot. Okay, that's all you need to know there. I just want you to have it in your mind that there's an inverse relationship between latitude and temperature. Okay, so make sure that's just should be intuitive for you, coming, you know, right off the tip of your tongue. High latitude, low temperature. Low latitude, high temperature. Inverse, opposites. Okay. You could have questions like this, just asking you basic geography, finding basic geographical structures around the globe. Okay, so these are the things you should know. Let me see if I can get this map so it moves. I want it to move back up there. Sorry, I'm messing with this thing here. Okay, let's put it right down there. All right, where is Japan, right? Japan's right here. So by the way this would look on the test is I would maybe mark something like this, you know, A, B, C, D, E or something. And I'd say, which is Japan? And you have to mark A, B, C, D, you know, whatever. That's how it would show up like on a multiple choice question. So hopefully that makes sense to you. But anyway, Japan's right there. I'm going to put A for Japan, right? Oh, I'm sorry. The L... that. Silly me. Sorry about that. I misread it. Okay, so where's the Aleutian Islands? The Aleutian Islands are these islands right off the coast of Alaska. We're going to talk about those. We talk about like plate tectonics and also talk about subduction arcs. Japan is another subduction arc right there, B. The Andes Mountains are right here, C. Kind of go all the way here along the west coast of South America. The Himalayas are here to the north of India. Okay. The Gulf of Mexico. Gosh, I hope you know where the Gulf of Mexico is. That's right. Yeah, you live in the Gulf of Mexico if you're taking this class. Hudson Bay is this bay up here in Canada. Okay, that's important when we talk about glaciers. Greenland is here, G. And Iceland is here, H. It's important we talk about plate tectonics. Sumatra is important when we talk about earthquakes and tsunamis. That's right there. The Philippine Islands are right here, J. And Lake Baikal is here. Okay, that's in Siberia. And the Atacama Desert is important when we talk about deserts. That's right there, right on the west coast, on the east side of the Andes Mountains, on the west coast of South America. Okay, so now you got all those. Just make sure you know where all those items are. Okay, because I could have you, well, I already explained it, so you understand. But anyway, let's go on to basic Earth structure. How old is the Earth in terms of when it accreted? According to, this will probably be worded like according to scientists, according to radioactive dating techniques, how old is the Earth? And it's about 4.5 billion years old. GA, I'm sorry if I put GA there. GA means giga-annum, means short for billion years. Okay, 4.5 GA or 4.5 billion years. Okay, 4 basic layers of the Earth. Oh, by the way, this is all stuff, very, very important stuff you should know. So, gosh, screwed that up. Okay, 4 basic layers of the Earth, right? You have the crust. You have the mantle. This is all mantle. Then you have the outer core. I'm going to put O core, and then you have inner core. Okay. Of those layers, which one's molten? It's just the outer core, and that's it. Okay. Mantle is not molten. The mantle convects. Yeah, it does convect. It has fluid-like behavior, but it is not a fluid. It's not melted. It's not a liquid. Okay. It's absolutely solid rock. Which of the 4 layers, what are the 4 most abundant elements in the whole Earth? You got to know that. That is iron, silicon, oxygen, and magnesium. That's the whole Earth. If you take the whole Earth. If you take the crust, you change out iron for aluminum. But everything else is the same. Aluminum, silicon, oxygen, and I'm sorry, I said the wrong thing. Magnesium. And iron. Okay, so magnesium switches out, not iron. Pardon me. What's the composition of core? It is iron, nickel, alloy. For the most part, about 95% iron, nickel, alloy. There is other stuff down there. It's a very contentious debate among earth scientists and geologists about what those other elements are that are in the core. Sulfur, carbon, silicon, oxygen are all kind of very, very possible contenders for what it is. But we know that there are lighter elements in the core besides iron and nickel. But we know that it's probably about 95% iron and nickel. Okay, maybe 5% other stuff. What proportion of Earth's mass is in the mantle, the crust, and the core? So, mantle's the big boy. The mantle is the Texas of the Earth. It's 2/3 of the mass of the Earth. The crust and the core is about 1/3. And you might be saying, Doctor, 2/3 of it is mantle and 1/3 of its core. There's nothing left over for the crust. And that's almost basically true. The crust is really only 0.6%. A tiny, tiny, tiny piece of Earth. It's important to us. We live on the crust. We see the crust every day. But it is not really a very big part of Earth. Only 0.6%. Dominant rock type on the ocean floor. Ooh, gosh, know that. That's basalt. It's a nice black rock. Okay, very plain. Fine-grained, aphanitic texture, black color, mafic, basalt. Okay. Know this one. Very, very important. I'm sorry I keep saying this, but these are just very important questions. Very, very important. What are the main differences between continental and ocean crust? Okay, density. Ocean crust is about 3 grams per cc. Continental crust about 2.7 grams per cc. You might be saying that seems like a small difference, but it's really a very important difference. It has huge implications for the structure of Earth. Even though there's just a small density difference, it's why we have continents at all. If continents had the same density as the ocean crust, we would just be sitting at a much lower level, and really probably, people are worried about sea levels now. If we had a density that was, same as ocean crust, you'd be really worried about sea levels. We'd be sitting much lower in the mantle. Average thickness, ocean crust is very thin. Okay, 5 to 7 kilometers. Continental crust is around 30 on average, but it can be up to 70. So it's less than 70 kilometers. Average age, ocean crust is young, continental crust is old. This is really on average only maybe like 50 million years old, whereas continental crust is maybe about 2.5 billion years old on average. Okay, very old. Average rock type of the ocean crust is basalt. Continental crust is on average intermediate. It's diorite or dioritic. Okay, composition, like I said, mafic here for the ocean crust, intermediate for continental. And the average elevation, ocean crust is -4 kilometers below sea level. Continental crust is about 500 meters above sea level. Okay, so that's that. What's the primary difference between mantle asthenosphere and mantle lithosphere? Asthenosphere means astheno means Greek for no strength. Okay, mantle asthenosphere is the silly putty of Earth. Okay, silly putty, is silly putty a liquid or a solid? Well, it's you might know silly. I hope you know silly putty. You can take it, you can bounce it against the wall. It's definitely a solid, right? You can even hit it with a hammer and crack it. But the thing about silly putty is it can mold and it can deform, right? Or think of maybe like modeling clay or something like that. Is it a liquid or a solid? It's definitely a solid, but it can bend and can deform. Okay, the lithosphere is not like that. The lithosphere, which consists of the upper mantle and the crust, is more like what you're used to with rocks. They break, they shatter, they are brittle. They're like a cookie, right? They just snap and break. Asthenosphere is not like that. The asthenosphere is the deep mantle, and the lithosphere is the upper mantle plus crust. Okay, so you got to go down on average maybe like 100 to 150 kilometers to get down to the asthenosphere. But there are some places on Earth where the asthenosphere comes right up to the surface. Okay, think Iceland. We'll learn more about that later. We talk more about plate tectonics. Okay, so moving on to matter, and then we'll talk about minerals. And it looks like we might just get through, probably we should get through minerals today, and then we'll be all done, okay? So matter. You should know your 3 subatomic particles and how they're arranged in atom, okay? So that's, you got the nucleus, right? And then you have protons and neutrons in that nucleus. Okay, there's my protons and neutrons in the nucleus, and of course around it there are orbits of electrons. Okay, just know also that electrons are negatively charged, protons are positively charged, neutrons are neutral, and also know that protons are much more massive than an electron. They're like 10,000 times more massive than an electron. So imagine if you're an electron, if you were an electron, a proton to you would be really, really big, really massive, right? So imagine 10,000 times your weight. Let's say you weigh, right, 150 pounds or 100. I'll make it easy and say you weigh 100 pounds. And you want to 10,000 times larger than you. That would be 1,000,000 pounds, right? So what would 1,000,000 pounds be, right? Be like, you're talking about something that's like, an aircraft carrier or something like that. So if you're an electron, a proton is like an aircraft carrier compared to you. Okay, you're talking about thousands and thousands of tons. I don't know, maybe aircraft carriers are even bigger than that, but you're talking about like maybe like a ship, something that's thousands of tons. So just be aware of that, right? Something to help you visualize. You should be able to describe the principal forms of chemical bonding found in minerals. Okay, so what were those principal forms of chemical bonding? We talked about ionic, and we talked about covalent. Those were the main kinds. We talked a little bit about, maybe a little tiny bit about van der Waals, but don't worry about too much about that. Van der Waals is weird. It's got 2 A's. It's a Dutch word. Anyway, ionic and covalent are the ones you should mostly worry about. Okay, ionic is when one one of the bond pairs, one of the atoms in the bond pairs, gives an electron to the other, or maybe gives electrons to the other. Okay, it's a give and receive sort of relationship. Covalent is not like that. It's more of a sharing relationship. So it's like atom 1 and atom 2 get together and say, hey, let's share our electrons, and you can be happy and I can be happy, both of us. And that's how they do it. Okay, so it's a sharing of electrons. Van der Waals are types of molecular bonds that occur at very short distances, and I don't want to get it has to do with like quantum mechanics. I don't want to get into all that, but just know that they're a type of kind of weak, very short range molecular bond. That's all you need to know about it. Anyway, you should be able to define the following terms. Covalent bonding, right? So bond involving, maybe I shouldn't write all this stuff out, but it's a bond involving the sharing of electrons. Okay. Ionization is, now that's a good question. Ions and ionization. Ionization is when you go from a neutral atom to an ion. That means you take on a net charge. So a neutral atom has a balance of electrons to protons, right? Protons are positive, electrons are negative. When it ionizes, those electrons are either lost or gained, and the atom takes on a net charge and it becomes an ion. So an ion always has a net charge. So it's an atom with a net charge. Ion is an atom with a net charge. Cation is an atom with an ion with a positive net charge. An anion is one with a negative net charge. An ionic bond, simply a bond between two ions. It involves the giving of an electron and the receiving of an electron, or I should say electrons. Could be multiple electrons involved in the exchange, but one gives, one receives. All right, last section, minerals. Please explain the criteria for being a mineral. There are 5 criteria. So, what are those criteria? You got to be solid. You have to be natural, naturally occurring. Okay, that means no synthetic minerals. You have to be formed by a geologic process. So you can't be a biologic process. So example, your teeth are actually mineralized material, but we don't count them as minerals because they're formed by biological process. That's why. Okay, number 4, we also have to be crystalline, have a crystal structure. So what is crystal structure? That means that your atoms are arranged in a pattern. So crystal structure looks like that. Okay, I'm sure you can all see the grid pattern right there. Okay, whereas a non-crystal structure, the atoms are just going to be, put willy-nilly wherever. Okay, so that's between that. It's atomic arrangement, ordered atomic arrangement versus disordered atomic arrangement. So crystals, minerals have a crystal, ordered atomic arrangement. Number 5, you have to have a definable chemical composition or definable mineral formula. So for every mineral, you have to be able to write down its mineral formula. Okay, you have to be able to take its composition and generalize it some way that you can write down a mineral formula that applies in every case for it. Okay, so for examples, quartz is SiO2. It's never SiO3. It's never Si2O4. It's never Si whatever, blah, 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 blah. Okay? Now, you can't say that about, for example, like wood or your body, Like I might have more carbon atoms than in my body than one of you, or more hydrogen atoms or something like that. I can't write a generalizable chemical formula for a human, but I can for quartz. So that's what that means. So you should be able to explain that in a paragraph. That's how that question would appear on the test. All right, hardness of minerals. the Mohs hardness scale. Goes from 1 to 10. Number 1 is talc. 2 is gypsum. 3 is calcite. 4 is fluorite. 5 is apatite. 6 is orthoclase, which is a type of, if you put potassium feldspar, that's fine too. 7 is quartz. 8 is topaz. 9 is corundum. And 10 is diamond. All right, now, that said, I am not going to have you write 1 through 10, all of those. But I could ask you a question like, what's the hardest mineral? Diamond. Of the following minerals, which is hardest? Calcite, quartz, fluorite. Quartz, right? That's the hardest. Of the following minerals, which is the softest? Talc, calcite, fluorite. Talc is the softest. Okay, so that's the kind of question you would expect to see on there. Okay. We talked about 8 different physical properties of minerals. Okay, and you should have some familiarity with those. Color, obvious, right? Streak, that's the color of the pulverized mineral, the powdered mineral, which is not the same as the color. It can be different. Hardness. Talked about hardness is the ability of the mineral to scratch, right? If it can scratch or not. Density. Cleavage. That's the tendency of the mineral to break along certain planes. Okay, they're patterned to the breakage. That's the way I think of it. It's where the crystal has broken. Okay, so cleavage. Crystal habit. The shape of the crystals. Some crystals are plate-like. Some are sharp and pointy. Some are fibrous or needle-like. Some are, whatever it is. Some are tabular. Some are prismatic. Some are cubic. Okay, different minerals have different crystal shapes. Okay, that's we call it crystal habit. I'm running out of things here. Color, streak, hardness, density, cleavage, crystal habit. Come on, help me out. What am I missing here? 8 is just kind of it's kind of a grab bag of like other properties. So those were things you might remember. We talked about things like magnetism, the smell, the taste, etc., etc. I'm missing something. I cannot for the life of me remember what it is. What am I missing here? It's going to come back to me after this. Okay, and I'm sorry, I have to look this up because I cannot for the life. I'm missing something and I can't remember what it is. Probably you all know and you're shouting it out there, but what is it? Maybe I haven't. Maybe it's too early. I haven't had enough coffee yet. What did we not talk about here? Color, streak. Of course, luster. Duh. Here we go, luster. So luster is how light reflects off the surface, right? If the mineral is very shiny, call it metallic, reflects off. It also describes how light penetrates into the mineral. If it's translucent, opaque, transparent, etc., etc. So it's how light interacts with the mineral. Okay. So those are the properties you should know. Silicate structures. All right. You might remember that we had 5 actually silicate structures that we talked about. There is the isolated structure. There is the single chain. There is the double chain. There's the sheet. And there is the framework. Okay. For isolated, that means the silicate tetrahedra are all by themselves. They don't touch. Okay? So there's isolated structure. That corresponds to olivine. Okay? Olivine is an isolated silicate structure. Single chain is when you have one linked up with the other. Okay? So you'll notice that every silicate tetrahedra in this case is sharing 2 of its 4 corners. Okay. Double chain is when you have basically two single chains linked together. Okay. So you have one of these linked like that. And I don't know how much I want to draw this stuff up, but anyway, you get the idea. But it's two single chains linked together. It's called double chain. Single chains are the pyroxenes. Double chains are the amphiboles. Sheet silicate is when you have every single silicate tetrahedron is sharing 3 of its 4 corners in these hexagonal sheets. Okay, so those are the micas. And framework, finally, is when all 4 corners of every silicate tetrahedron are being shared with another silicate tetrahedron. That's the feldspars and quartz. Okay. You should also know the formulas for quartz, olivine, calcite, and hematite. Those are 4 minerals I'd like you to know, their chemical formula. Okay, quartz is, I'll just write them here, SiO2. Olivine is FeMg, SiO2, SiO4. Calcite is CaCO3. Hematite is Fe2O3. Okay. Now, the most common carbonate mineral of the crust is calcite. Okay, CaCO3 is its formula, like I said above. Which mineral fizzes with acid? Guess what? It's calcite. So that's a mineral that's very susceptible to acid. You should also know the most common mineral of the crust. That is feldspar. I notice a lot of people on the lecture assignment put quartz. And although quartz is very, very common, second most common probably, it's not as abundant as feldspar. How do you tell the difference between silicate minerals and non-silicate minerals? What's the difference? Very simple. Silicate minerals have the silicate molecule. Remember those beautiful silicate tetrahedra? Okay. You should know, by the way, what a silicate. We'll talk about that next. We'll talk more about silicate in the next one. But they have silicates. Non-silicates don't have silicate molecules in them, right? So, for example, SiO2, quartz, is that a silicate molecule? Yes, it is, because you can see it has silica in it. Okay. How about calcium carbonate, calcite? Is calcite a silicate molecule? A silicate mineral? No, because you can look at the formula. It does not have silica in it. Okay. Silicate minerals are often, not always, but often harder than non-silicates. Okay. They can scratch really easily. They're very hard minerals. All right. So that's all I have for you. Been going on 52 minutes, so I better shut up now. And you have a lot to digest and think about, I'm sure. So we will begin this next time with a part 2 of your midterm study guide. Good luck studying for your test. Let me give you a couple hints before you go. Flashcards. My best students who do best on the test almost always make flashcards of all these different questions. And even if you don't study with the flashcards, just making them helps. Okay? So anyway, I'll bid you adieu. And good luck studying for your test. And don't forget to watch the next video, number 2, which will go through the next half of this study guide. See you next time.